Okay, so here we go. Worksheet 7.4, numero 60. So, just un poco. Let's see. So, it says the potential energy of a 0.2 kilogram particle. So, my mass is 0.20 kilograms. And then it gives you this. So it tells you that the potential energy as a function of x is, I'm going to drop my units because I'm lazy, it's 8x squared minus 2x to the fourth. All right, assuming the only force on the particle is the conservative force responsible for this potential energy, when the particle is at x equals 1 meter, what is the magnitude of its acceleration? Okay, so this is another problem where we need to find two ways of thinking about the same thing. Okay, so somehow I need to get from potential energy to acceleration, right? Okay, is that a question, Peter, or a suggestion?
A suggestion.
Okay, cool. What do you got?
You go through force.
Cool.
That's the thing of those the two.
Awesome. Awesome. Yeah, so look, so kind of like Adam and I were just talking about before. In the last problem, I gave you force, and you had to integrate to get to work and energy, right? This time, you're given stuff about work or energy. So instead of integrating, we differentiate, and that'll get us to force, right? And you guys agree that force is also related to acceleration?
Yes.
Okay, so somehow, that's sort of the path that we're going to take to solve this. Okay, that's the thing that connects them. So, over here, let's see. How can well, I think Peter just answered this. Does everybody understand? So this is my equation for my potential energy. So the force should be the derivative of that, right?
Yep.
So my force should be the derivative of the potential energy with respect to x, right? So that's the derivative with respect to x of 8x squared minus 2x to the fourth. So that is what, 16x minus 8x cubed?
Yep.
Okay. So now I know my force as a function of position can be expressed as 16x minus 8x cubed. So my force when x equals 1 meter would just be plug 1 in, right?
Yep.
Isn't that what it says when x is 1 meter?
Yeah.
So plug in 1 meter, 16 times 1 minus 8 times 1, so you get 8. It's force, so it's got to be newtons. Oh, and now I can find my acceleration, right? Yeah.
So I thought that work was the opposite of potential energy.
Yeah.
So what I did was take.
Oh, wait, no, oh, yeah, you're right. I have my signs mixed up, don't I? I have my signs mixed
But
up.
I got a negative 40 for my answer.
Did I not put that on the answer key?
No. So
All right.
I don't know what it was.
Let me double check. So here's, I honestly don't remember offhand which way it is. So I'm going to figure it out real fast. If you forget where that negative goes, you can do what I'm about to do. Because I'm honestly not sure. I got to double check. So look, I know this. I know that for a spring, it's this. And I know that my elastic force is negative kx, right?
Yep.
So if I differentiate this, does it give me this?
No.
No. Oh, shoot. So,
Aha.
so I need to add in a negative sign, don't I?
Yeah.
Does that make sense?
That's so whack.
Okay. So how could we have gotten to that a little more efficiently than me kind of bumbling my way through it that way? Oops, I went the wrong way here. Oh, I know. I have the equation on. Shoot. I get enough minus for this lesson. Can I rewind for a minute?
Yep. Yeah. Sure.
Mr. Hacker.
Yeah.
since you know that the negative change in potential energy is equal to the integral of force, don't you just plug in u and just have the negative sign?
Yes, that's exactly what you do, and I'm just trying to figure out the most efficient way to write that to help you guys understand that. But yes, that's exactly where I'm headed. It's exactly where I'm headed. So my problem is that this equation that I wrote here is not accurate. All right? Because the force isn't equal to the derivative of the potential energy with respect to x. It's equal to the derivative of the work done by that force with respect to x.
So would it be change in u?
So it's, yeah, I mean, it's this. The work done, oops. It's this. The work done by my conservative force is equal to the opposite of the change in the potential energy due to it, right? So what I probably should have written, I'm going to rewrite this page. I'll do it in blue. So I probably should have done this. Force equals the derivative of the work done by that force with respect to x, which is negative du dx, and then gone from there. And I think that probably would have been the easiest way to get through it. Peter.
Although, like, let's say the problem was to give you like two values of u, and like one of them wasn't 0, because like the initial like the change in u is goes from like being 0 to like whatever the value of 1 is. So like would we then have to like plug that into du instead of like just taking the equation that we have? If that makes any sense?
I know what you're getting at. I tell you what. Let me finish the problem as it's worded.
Great.
And then let's come back and investigate that, because I'm honestly not sure. All right, so is everybody so A, I apologize about the little glitch here. This was wrong. Is everybody okay with this little cleanup here?
Yeah.
Okay, so then we want to take the derivative of this with a negative sign, right? So this is the derivative with respect to x of negative 8x squared plus 2x to the fourth, which gives you negative 16x plus 8x cubed. So f of x is that, right? So f at 1 should be 8 newtons, negative 8 newtons, sorry. And so now we can find our acceleration. The acceleration should be the force over the mass, so that gives you negative 40 meters per second squared. Is that the answer I had on the sheet? Fingers crossed?
It's positive 40.
I am positive. Oh no. Oh, aha! Oh, you guys are going to be mad. Yeah, the question says what's the magnitude.
Oh my god.
Sorry. I know, I totally need to let that.
Seriously, that was bad.
Alright. Okay, so are we good?
Yeah.
Okay, I would just take points off or something like that. And I know they don't on this AP scoring either.
They don't.
Yes.
I have a quick
If it says magnitude, you leave the negative in it.
So, in 6 it tells you that the force is conservative, and since the potential, like the equation for the potential energy isn't linear, does that automatically make it a spring?
No.
No, what does it make?
Oh, we don't know. It's some theoretical, weird, mysterious conservative force.
Okay. Sounds good.
Okay? Yeah. And well, I mean, it could be a spring. It's not an ideal spring, because if it was an ideal spring, then it would have to be 1/2 kx squared.
Good, so since we don't know if it's a spring, we can't really use 1/2 kx.
Correct. In fact, you know, so 1/2 kx squared is the expression for u, like the letter u, right? But the problem tells you that the expression for u is this, which is clearly not 1/2 kx squared, because there's also this other term. So, do you know what I mean?
Yeah, I know.
Okay. All right. So,
Is 7 important?
hold that thought for 1 second. I want to get back to what Peter was asking before. So, Peter, you were saying.
Because like in this question, if you were to plug in like, u of 0,
But we never had to do that in our solution to the problem.
like if you take the derivative, like if f is equal to negative d, like it says negative du, but wouldn't that be negative d change in u over dx?
But that's when you write when you write dW or du, that's what that means. That means change in. But it's just, you're just talking about a...
Okay, yeah, I'm there now. Yeah, sorry.
No, that's okay, because I'll be honest with you, that was, when I was processing this and starting to write it out, I was processing. Is it okay to just put that negative sign there?
Yeah.
And it's not obvious, but I do think it works.
All right, cool. Thank you.
Yeah. All right, so I think the big lesson we're getting here, I think that we had, I think both in number 5 and here, we had this issue with the negative signs. Okay? So what you need to remember is that when you integrate, the relationship, the calculus relationship between force and work and energy is the work relationship, right? It's not energy. Okay? And if you want to go to energy, that's when you got to stick in the negative sign. Okay? All right. Is 7 important? Oh, can I say one other real quick thing? Do I want to go here? Let me do one other real quick thing. This is a side note, but I think an important one. So yesterday I made the comment that this is the first time that we've done calculus. Like usually our horizontal axis is time, right?
Mm-hmm.
And this is the first time we've run into problems where your horizontal axis is x, right? So a moment ago we just came up with this expression. F of x equals, what was it, negative 8x squared plus 16x cubed, was it? I guess I could just look. Oh my gosh, I get an F minus. Negative 16x plus 8x cubed. Negative 16x plus 8x cubed. All right, so everybody agree with that?
Yeah.
All right, now we also knew the mass, right?
Yes.
So do you guys agree? I ought to be able to do acceleration as a function of x by taking my force as a function of x and dividing it by the mass, right?
That's just a scalar.
Yeah, right. It's just acceleration is net force over mass. Thank you. All right, and so we knew the mass here, right? The mass was what, 0.2?
Yeah.
Follow? All right, so look, if I divide all of this by 0.2, you end up getting negative 80x plus 40x cubed. So that's an expression for the acceleration as a function of x, right? Good. Now, the problem wanted... Oh, shoot, this isn't going to show what I wanted to show. All right, so is everybody good with that? I still don't have the... Yeah, okay. So question, suppose I wanted to know the velocity at a certain point. Suppose I wanted to know the velocity at a certain point. Could I just take the derivative of that and then have an expression for velocity? You're saying no, Seba, how come?
Because you have to add c.
I'm sorry, I did the same thing again. I keep saying derivative. Could I just take an integral of that to get the velocity?
Integral is just a change in velocity, so you need to have a c at the end.
That's not the only problem. It doesn't. My question has nothing to do with the c.
I don't know.
So what's the connection between acceleration and velocity? What's the calculus connection between acceleration and velocity?
Velocity over time, and this is position.
Acceleration is the derivative of velocity with respect
To time.
to time, right?
And this is position.
These are not t's, they're x's.
Yeah.
So when I integrate this, if I take the integral of acceleration with respect to x dx, that doesn't give me anything. It's sort of meaningless, right? Because think about what units I'm going to get. I'm going to get meters per second squared times meters. Right? So you get meters squared per second squared, which is absolutely not velocity. Follow? Because remember, that's area under a curve. So if I give you acceleration and position, acceleration is in meters per second squared, position's in meters. If I find the area under some chunk of that, is that going to give me meters per second? No. You see what I'm saying?
Yeah.
All right, so this is an issue that I remember people having last year, was they would try to use calculus when the function wasn't written in terms of the right variable. So you gotta watch out for that. Am I making sense? What does that make sense?
Yeah.
Everybody, does that make sense?
Yep.
Okay, cool. All right.
Problem is you just use X as like the generic variable.
And I don't write down T, so I usually just use